Yeah, that'll work.
Okay, yeah. Well, so that's what happens when you have 4 screens connected. So, um, well, thank you very much. I appreciate your patience. Gonna start here. So I'll be talking about the CR landscape, systems, service providers, technology. So my name is Jacob Fosso Tande, as Henry said. I am a research computing administrator at the University of North Carolina, Greensboro. It's a pleasure for me to share this with you. So there is a lot to talk about. So we can cover everything, but I'll just go selectively through the CR landscape, look at services, service providers, technologies. But before we get there, so just a quick outline of what we'll be looking at. So we'll explore the NSF exit. We're moving from exit to access systems. And a few of them, there are many of them, but we'll just pick a few, especially the new ones. Anvil, Bridges 2, Expanse, Jetstream, Frontera, and then look at the Open Science Grid briefly. We'll look at the science gateways, the Department of Energy National Labs. I'll focus on Oak Ridge Leadership Computing Facilities, Summit and Frontier, and then the NERSC, Perlmutter and Cori. And then we'll explore ESNet and Epoch, look at Internet 2, and some international organizations, specifically GEAN, Compute Canada, and PRACE. And finally, we'll complete with tools, Cyberinfrastructure tools, Globus, XD Mode, Open on Demand, ArcCI, and many more. So I'm pretty sure you have your definition of what a cyber infrastructure tool is, but we'll take a look at that and we'll see what everybody thinks. So first, because of the expanded landscape and the limited time that we have, and we'll only have to look for a way to strike a balance and only touch on a few systems, as I said initially. We'll focus on where to find those systems because of this limitation. So I won't be able to cover some of the systems: NSF, Access, Darwin, Rockfish, Open Storage Network, Stampede 2, FASTA. There are many more. Or the Department of Energy Lab resources. There are 23 national labs, and a majority of them do have HPCs with different criteria on how to access. So my focus is on those that are readily available. We're not touching on the NIH resources, no cloud resources such as Cloud Bank, Cloud Lab, commercial cloud as well. We're not touching on that. Those could be topics on presentation by themselves. And of course, the regional network. So we just focus on Internet 2, but there are other regional networks that we're not going to focus on. So, yeah, so the question that comes to mind is why even bother? So see the number of questions there, chat in the box. Okay, yeah. So why even bother about the infrastructures? So you should bother if you are from a resource limited institution. So you don't have the large computing powers that some of the R1 and R2 institutions have. You rely on this national cyber infrastructure system to service your users, or your users have needs that are not present at your institution. You could be from a well-resourced institution, but it doesn't imply that you have all of them. So for example, if you could have users with extreme memory compute system, they need that, you don't have it. They need to test applications, performance, or some sort of hardware that you may not have at your institution. So it'd be good to know where some of these infrastructures are. You have distributed data sharing, like open storage network that you may need, especially for highly collaborative projects that your users may have. Or sometimes your demand surpasses offer. So you have resources, but at some point there is high demand, especially during peak research period. Or you have highly collaborative research projects, which you have researchers from multitude of institutions or from many countries trying to use those resources which your institution may not be able to provide or give access to all of them. I'm thinking here of the IceCube project or the Event Horizon Telescope collaboration, which we recently have the fruit of such collaboration and use of resources available with the first image of a black hole. So I'm going to ask you this question: what is more important, knowing all about the system and services or knowing where to find these systems and services? Share your thoughts in the chat. As far as I'm concerned, I would like to know where to find these systems and services, because if I know where to find them, and I can figure out what is important to me or what my user need or what is important to my users. Even though sometimes you may have an idea, and then when you really go into the system, you end up figuring out that it's probably not what you want. So what do you think? Have a chat here. I need to select the slide windows to share. Okay. Oh no, that's old message. Know where to find. Yeah, that's true. I agree with that. Where to find. So, okay. I think the next, we're going to focus on startup allocations, which is really the very important place to start, especially when you're trying to explore some of these resources. And there's a reason for startup allocation. So exit resources, they have startup allocations, and there are a number of them. You could have a startup. If you're a campus champion, you have a campus champions allocation that you have access to. I am a campus champion, so I have access to the champions allocation, and I use that to the benefit of my users. So why would you need a startup to get a startup allocation? So you have small scale computational activities that require the unique capabilities of resources allocated through exit. So it's small scale, you need to start somewhere. Application development. So if you developing application, you need to test, run, and maybe you want to test your application on HPC, you don't have it, you want somewhere to test that application, you get the startup allocation. Benchmarking, especially for evaluation and experimentation, before you get a very substantial allocation for production activities. Or you're developing a science gateway, as we'll see later on. If you're developing a science gateway, you need to make sure that it meets the requirements of your user. So you may want to get a startup allocation. So if you want to get a startup allocation, you will go to the Exit user portal. This will be changing to Access. There you have all the information you need for a startup allocation. This is for the NSF Exit Access system. So the startup allocation, so share your thought in the chat if you have or you had a startup allocation. How do you or would you use the startup allocation? So for me, my startup allocation is a great way, especially the campus champions allocation, is a great way for me to explore the various systems that are available. I use my startup allocation. I have access to a number of them. I will go into each of the allocations, see what type of software they have, what type of system is available, type of memory. So if I have a user, I can have an idea of where to send them. And sometimes I can add users to my allocation, a number of them, and have them play around. If they figure out something that they want, then we'll go ahead and have them apply for a startup allocation for themselves. So how do you use your startup allocation? You may want to share how you do that in the chat. Yeah, can't know everything. So I'm going to start with the very first HPC or Exit access system that I've chosen to go over. And this is Anvil, the Anvil HPC, which is which has a symbol, produced border marker. So it's at the at Purdue University, and it's a category 1, a national composable advanced computational resource. So it's composable, so you can adapt it to various needs. It has a 5-year production operation, and it started in February of 2022. So the Anvil HPC. So the Anvil HPC ecosystem, it consists of state-of-the-art CPUs and GPUs. It has composable system. It has a software ecosystem, training for users, and then an interactive computing environment. So the compute cluster has 1.1 billion CPU, makes available 1.1 billion CPU core hours per year. And the composable subsystem is complement the batch computing, which is what most of us are used to. So the Anvil subsystem, so as we said, there's the high performance compute nodes, and then we have the composable subsystem, GPU, large memory, and storage. So the high performance compute system has 1,000 compute nodes, mostly the 3rd generation AMD EPYC processors with 5.1 petaflop peak performance, 8 large memories, storage nodes on the composable system with possibility to switch to Kubernetes. You could equally go into cloud bursting to Azure. And you have a 16-node, the GPU, the large memory GPU with 16 nodes for NVIDIA A100 GPUs each. And of course, you have storage, which you will need for a system like this with about 10 petabyte of parallel file system and access to globals for data transfer. So Anvil, other than the hardware, you equally have at the application level. So you have programming libraries and compilers, various programming languages, Intel, AOCC compilers, message passing library, and various types of workflows. You have the scientific applications that you will have for most systems, but specifically those that meet the needs of Anvil's users. You have containers and data sets. Anvil specifically has support for Singularity. That would be the container that you have on Anvil. Next, it's Bridges 2. And please, if you have questions, feel free to stop me and ask your question, or you can text in the chat. I see that there is a message in the chat. What is the memory CPU on Anvil? So Anvil, I think Anvil has, sorry about that, Anvil has a number of, so Anvil has a number of nodes with different memory requirement. I don't quite remember the specificity of Anvil memory, but I think they're good enough for you to do scientific simulation. So if you check the website, you have a definition or the description, the specificity, especially the memory size of Anvil nodes. So Bridges 2 is the successor to Bridges. So it has a number of improvements relative to its predecessor, Bridges. Specifically, you can do more science, approximately 3 times larger than Bridges was. Faster computing CPUs, especially the AMD EPYC processor, which seems to be the standard of the day. You have faster storage, fast flash arrays. You can do smarter science. It's more scalable. And of course, it provides transformative capability for rapidly evolving computation intensive and data intensive research. So Bridges is located at Carnegie. It's managed by both Carnegie Mellon University and University of Pittsburgh. It looks like there is a question here in the chat. Okay. So Bridges to look at the core concept. So it has a converged high performance computing plus AI and data. So it has custom FAT3 closed topology optimized for data-centric HPC AI and high-performance data analysis. So you have heterogeneous node types for different aspects of workflows, CPUs, and AI-targeted GPUs, 3 tiers of per node RAM, 250 gigabyte, 512 gigabyte, and of course, the very big one, the 400 terabyte memory. You have extremely flexible software environment, community data collection, and big data as a service. So it has a number of innovations beyond Bridges, as we saw in the previous slide, especially the AMD EPYC processors with very fast compute capabilities. So Bridges to architecture. So you have the standard architecture with the interconnect, but what is noticeable here is the web server nodes. There are 6 of them. So you can have a web server on this node. You have a database node, 12 of them, data transfer nodes, 2 of them, login node, 26 of them. So, so those are the interfaces, how you get to that, Bridges to. You have the file system and you have the management nodes. There are 12 of them. And really important, and I've had some of our users use Bridges to, especially the regular memory nodes for computational chemistry purposes. It has 488 of them with 256 gigabyte of RAM. You have the large memory nodes with 512, and of course the extreme nodes with 4 terabyte RAM. The GPU nodes, there are 24 of them for 512 gigabyte of RAM. So other than the hardware and the network fabric, you have a number of applications. These are a few of them that I have here, especially Open on Demand, which is really, my users really appreciate that. So they can access the HPC just the way they would do with their desktop. You have the Jupyter notebook, NVIDIA, TensorFlow, Caffe 2. And so popular languages such as Python, Anaconda, MATLAB, Java, Spark, and Hadoop. An AI framework, TensorFlow as well. So this is really a system that is dedicated for what big data analysis, as well as scientific physical science simulation. Next, I have Expanse, which they have their slogan, computing without boundaries. Expanse, the name explains, gives you an idea of what it is. It's an HPC resource, data-centric architecture, designed to serve the long tail of science. It has innovative operations, composable system, remote CI integration, so you can access remotely, and you can integrate it to other systems that are available in the cyber ecosystem. I see questions. Yeah, thank you, Henry. So the Expanse scalable compute unit, which we'll refer to as, is the SSCU, which is actually the San Diego Supercomputing Center Scalable Compute Unit, is designed for the long tail jobs, a mix of systems. As we can see here, the components have 56 CPU nodes, 4 GPU nodes. The CPU nodes are mostly AMD EPYC, at 2.25 gigahertz, and PCI Gen 4 256 gigabyte DDR4 and 1.6 terabyte NVMe disk. And the GPU nodes, 4 GPU nodes, mostly they are NVIDIA 100 and 32 gigabyte of memory. And of course, you have the network fabric that connect all of this. So the expand connectivity, so it's expand, so it's an adaptable HPC. You can adapt it to the needs and requirement. You can connect it to other systems. So it's set up, it has a really good network fabric, 200 gigabits per second between the data movers, which I suppose has globals or applications designed to move data, and to the compute cores. So you have object storage, 7 petabytes, and connected to the performance storage of 12 petabytes with a 200 gigabits per second network fabric. And it's connected, it has an external network that links it to other systems with really good performance. You can have access to Amazon, so there is that capability for cloud bursting. You can equally connect to other community infrastructure such as Open Science Grid, IT2, and as well as community instrument such as the cryo-EM or sequencers or other labs. So the composable system is actually the interesting one, which here we see a mix how Slurm and Kubernetes are used together for load balancing. So if you have a huge need on site managed by Slurm, so if Kubernetes has a number of nodes that are not in use, they can be pushed back to Slurm and vice versa. And all of this is managed by the Bright Cluster Manager. So the system is composable, so it supports complex distributed workflow. So making expand larger CI access to larger CI ecosystem. So you equally have user support for advanced user support if you need this composable system. So it'd be great at some point to have, I've had to sit in on a presentation on Expanse, especially when it was launched. I think this was really an interest. This is the part I like most about that presentation, the composable aspect of Expanse. So the cloud integration, yes, as we said, you can burst into the cloud, and Expanse support integration with public cloud. It supports projects that share data, need access to novel technologies, and integrate cloud resources into workflow. Users submit directly via Slurm or part of a composed system. So if you connect, if you connect to Expand through the Open Science Grid, you can submit directly from your desktop, and you get access to Expanse. You have options for data movement in the cloud, remote mounting of file system, and many more. Jetstream 2, I'll say that Jetstream 2 is the NSF equivalence of cloud computing. So we have the public cloud, Amazon, Azure, and so Jetstream is the NSF version of those. And so Jetstream is the successor to Jetstream 2 is a successor to Jetstream. It's mostly built as infrastructure as a service, relying on OpenStack, and storage is assured by self. And users can get access through a number of ways. You can use the OpenStack command line, or Horizon, or Atmosphere, And authentication uses the you have authentication service, and it uses the exit accounting system, and you have access to third-party clients as well as science gateways. So the JetStream architecture, so you have the OpenStack, you have the user gateway, as said previously, Atmosphere user interface, Horizon web dashboard, we'll see one of those, Atmosphere and OpenStack command line interfaces, third-party application, and we have language binding. So the OpenStack, the primary infrastructure is on OpenStack, and this is composed of what? Compute service, storage service, which is mostly through self, a network fabric, and you have an authorization right underneath those, and you have compute nodes, 500 plus, right below the authorization level. And on the secondary, you have orchestration, containers, databases, bare metal, and data processing as well. So this is a conceptual and architectural diagram for the systems environment. So JetStream 2, it's not it's not located at a single institution, but multiple institutions. So the primary institution being Indiana University, which has 416 nodes with 53,248 cores and 224 terabytes RAM in total. Storage nodes, 96 of them for 15 petabyte of storage. It equally has accelerators. So you have the Cornell University, which constitutes the regional hub, just as you will have for Asia or the GCP or other cloud providers. So they have regions. So JetStream equally operates in regions. So, and the regional systems, so one at Cornell University, you have the other at Arizona State University, University of Hawaii, and Texas Advanced Computing Center as well. So, and these regional institutions serve the needs of users closest to them, but I think you could equally, from one region to the other, still have access to it. It's a cloud, so you don't actually have a feeling of what is happening. So the regional systems have different types of nodes, mostly. So for the University of Hawaii, we have 8 nodes, about 1,024 cores, and this is similar with Arizona State University and Cornell University, but the biggest share is at Indiana University. So JetStream 2 capability. So this is a screenshot of my account on JetStream 2. As you can see, I have access. If I needed to create, spun off a virtual machine, I have a number of options. I can have a tiny M3 small, or M quad with a choice of CPUs, RAM, or root disk. There are no ephemeral disk as you will have for other cloud providers. So I could choose one of these, and I think this is pretty generous given how much SUs you have. You can really do some good work with this. So JetStream is mainly set up to enhance infrastructure as a service. It improves orchestration, support elastic virtual cluster, as well as federated Jupyter Hub with a commitment to 99% uptime, which is really good. Critical for Science Gateway hosting. So if you're thinking of setting a Science Gateway for your institution or region, JetStream 2 will be a good place to get resources to set up that or to develop that. Has hybrid cloud support, revamped user interface, much better user interface compared to Jetstream, unified instance management and multi-instance launch. And of course, it has greater than 57,000 cores of next generation AMD EPYC processors and a very substantial amount of GPUs, A100. I quite remember with Jetstream when I was looking for GPUs and hoping to get some allocation for researchers at my institution. They didn't have enough. So I think this time around, there is a substantial amount of GPUs and 18 petabyte of storage, 100 gigabit Ethernet Melanos network. Any question? Do you have some experience with Jetstream or any other system that you would like to share? So how do your users appreciate the availability of these resources? I personally, so I do have I have allocations of some of these systems, and my users generally appreciate the system, especially those that I give access to a number of them. Anvil, Expanse, just add them to those resources and let them explore the system, and they always come out really happy. But there is a downside to doing that from my experience. So you have a graduate student who's probably using the HPC for the first time, and they have an application. Because they've heard that the application runs in parallel, they can allocate a significant amount of nodes and hope for the best. But then they look at the job, it doesn't complete as fast as they thought it would complete. And then they come back to you and they say, well, I was using 10 nodes and I didn't see any difference. That is my story. So do you have something to share? What applications are you using to benchmark the selected allocation? Oh, okay. So these are not my system. So in an ideal world, we would love to have representative from all these service centers come and talk about their systems. So they do benchmark their system, I believe. They have support service if you need. So I'm just giving a rundown of these systems that are available to researchers. I don't manage any of these. In fact, at my institution, I only have, some departments have HPCs, but university-wide, I use a flagship university, which is UNC Chapel Hill cluster to help my users and other national cyber infrastructure that are available. So generally, I will go through the systems, look at the architecture, the type of applications they have, and then what type of application my user wants to run, and then set them up with the system that meets their needs. And I'll help them get started. If they run into difficulties, we'll try troubleshooting. But sometimes there are certain needs that I cannot provide, so which the center is best placed to provide. So we'll open a ticket for help. So to answer your questions, I do not manage the system, so I'm just giving a quick review of the system. So, but for benchmarking, I think each researcher and the application will do the benchmarking for the application. In the ideal world, the center normally will benchmark the application, and if it is an open source and they have the technical skills and the people are available to do that, maybe they can improve the code's performance and have you run on it. We'll see that later on with the Department of Energy, how they handle that. Okay, so that was Jetstream. So Frontera, yeah, this is TAC, Texas Advanced Computing Center. This is huge, really big computer with a lot of nodes, total of 8,360. As a graduate student, I spent a lot of time at Oak Ridge National Lab, but when I walked into this building and when Frontera was still being set up, this was huge. So 8,368 nodes and clock rate at 2.7 gigahertz, maximum turbo if you have 4.0 gigahertz with peak memory bandwidth of 282 gigabits per second, and a lot of, you have L1, L2, L3 cache and local storage as well. So Frontera, it's pretty much your standard HPC system, contrary to what we saw initially. So it has the login nodes, and there are 3 of them, and a typical compute node and other specialized compute node as well. So you have a home directory partition, work partition, and scratch partition, and scratch scratch partition, all of that interconnected through a network fabric, which Mellanox InfiniBand interconnect. So the login nodes are configured similarly to the compute nodes. So Frontera has a software stack, and as you can see here, is heavily tilted towards the sciences. I can see a number of very common applications, and this is just a few, a whole list you find on the website, or if you have an account, you log in and list the applications that are available. So you have GROMACS, NAMD, MATLAB, NW, or Northwest Chem, as some people call it, VAPS, which is pretty much popular for material science. You have Tensor, you have Caffe, PETC, and other scientific applications. So this is just a few. So Frontera equally allows you to run containers, and their container of choice is Singularity, but you can build Singularity on your local computer and upload it into Frontera. And if you don't know how to do it, I think they have staff in place, they will help you with that. It looks like I have something in the chat. Also interested in how people are managing software, Spark, Easy Build, Homegrown, and okay, yeah. So question, efficient and effective use of resources. Share your thoughts in the chat, okay? State observed habit adopted by your users that have resulted in a wasteful usage of resources. So what steps have you taken to reduce its occurrence? I know this is something that happens even with people who have been using these HPC resources for a very long time. There's still things that they do. We can't keep reminding them of what they need to do to preserve. Just because you have access to HPC doesn't mean you're going to use all the resources. I mean, so if it is high performance, you have to be able to use it efficiently, effectively, and it's reliable. So efficient and effective use of these resources. So I have my experience at my institution. Somebody gets a startup allocation, and within a few days, they are already in the red. They've gone past the allocation limit. So what have you observed at your institution? What are some of the ways that your users approach using these resources that result in waste? Have you figured out a way to reduce this? If yes, share with us in the chat. Okay. Requiring large memory node when they don't actually need it. Yeah, I agree with that. And actually, so I think I've had a case where somebody comes to me and they say, well, my research group is going to be doing some computation work, and we have a lot of data. We want to just make sure that the systems that are available will help us do that. And I go and I ask, how much data do you know your data size? What is the size of your data? And I hear 16 gigabytes. And I say, oh yeah, that's fair. That's fairly good enough, a good amount of data, but I think we can handle that. So people have the notion of large versus big. So when you say large data, I'm expecting to hear in the neighborhood of terabyte. So with the edge, we move on from the high performance computing, superclusters, to the community ecosystem, which is greatly represented by the Open Science Grid. It's actually now they've rebranded, I think. It's OSG consortium, and it has 3 components, specifically 3 components, including the main one. Let me take a look at the chart. Use training to max time and integration to the laptop, make a flawless laptop to mainframe. Yeah, I agree. So the OSG consortium has 3 components, and the one that we are very used to is the Open Science Pool. They've named it Open Science Pool, which it provides researchers with fair share access to computing and data capacity powered by distributed high throughput computing technology. So multiple institutions, if you have some compute resources at your institution that you want to connect to the OSG, they will help you set that up using the application for load balancing and submitting jobs, and you have access to these resources, and your users equally have access to the resources that are available on the OSG. And you equally have the Open Science Data Federation. I think this one is new. It enables users and institutions to share data files and storage capacity. So this makes them both accessible on the distributed high throughput computing, such as the OS pool that we just talked about. And the third pillar is the OSG on all hands-on meeting. This is a gathering of stakeholders. It provides consortium stakeholders and broader DHTC community with venue to share ideas and exchange information. So the OS pool, which is what we really used to. So as you can see, we have a number of institutions contributing to this pool, and you can have access to that. If you have an account, I have an account on OSG, you can request an account. They usually they have a number of workshops that they hold throughout the world, hands-on. You can have access to that. You can get to the workshop and learn how to use these resources, or you can ask questions on how to be part of it. So if you want to organize, for example, all the servers that you have in your users closet or that are scattered around your campus, you want to consolidate all of that to make good use of those resources. Yeah, OSG will help you with that, and you can equally contribute to the pool. So if you have excess capacity, yeah, you contribute that, and other users from other institutions will have access to that. So this is a fair distribution of this is just a snapshot. There are so many institutions. I just took a snapshot of a few. As we can see, Lancium is about 4 million core hours contributed to the OSG. You have from millions to about thousands of them. So every bit of compute resource is important. So the OSG is open to all. It's open to provider at all scale, from small colleges to large national labs, open to users communities at all scales, from individual students to larger research communities, domain science, specific, campus specific, across many domain science, open to any business model. So sharing, allocation, purchasing, and preemption is an essential part of the operation. So as I tried to take a look at the dashboard to see some distribution of core hours utilization by various NSF field of science. And so as you can see, physics stands at 46.77%. You have mathematical sciences, 12.23%, and astronomy, 21.92%, engineering, computer science at 1.06%. It's quite interesting that physics really stands out. So I'm not sure why this is so, but looking at the data, it appears to me that the Fermi lab contribute to the OSG, and I think they do a lot of computing that is related to physics, and they share a large amount of their resources as well. A very good amount of their compute resources is contributed to the OSG. So that may explain why physics stands out. So the OSG consortium, so compute resource consolidation. Okay, again, share in the chat. So have you consolidated compute resource on your campus? What are the benefits of such an initiative? Yeah, this is interesting. I know at my campus, so various departments have various resources. And so everybody operates in their independent island and they don't share. And sometimes these computers, they sit idle, nobody's using them. So it will make sense to consolidate all these resources and make available to the wider community. I think there is a lot to gain by consolidating rather than operating at individual level. Have you considered using, I don't know, so can you please share the source reference for this data? Oh, okay, so I think somebody shared that. So if you go to the, I'm not sure whether that was related to the OSG. So if it is related to the OSG, you can go to the OSG website and they have the dashboard. You can have all the resources utilization available. You can have them by institution, the pools that are contributed, or by the science field as I indicated below. Okay, good. So share your thoughts in the chat if you've consolidated or if you've thought about consolidating compute resources on your campus. So to round up things, so the NSF exit access system. So if you went to the exit site, you will see allocated resources, which is you will see allocated resources, which generally describe the resources and the recommended use. So not all of them have the recommended use. So sometimes you have to figure out how you want to use the resource at your institution. So you have non-allocated resources, and that tab provides information about other resources in the exit ecosystem. And so you have allocation request, general information about the resource allocation, how you can request allocation of those resources. And of course, there is a link to the information. So this presentation is being shared. The slides are available, so you can have access to that link. And if you haven't yet, you can request an allocation. If you're a campus champion, you can have access to the champions allocation. So I understand that the campus champion allocation probably will be going away when access kicks in, but still, if you had an allocation, you keep your allocation. You probably will have to adapt it to the new format. I see here a chat. Okay, we consolidated about 4 years ago, though not require, has been fairly successful. Oh, yeah, that's good. Thanks for sharing. So next, we go to the Department of Energy National Labs. So there are about, I think, 23 national labs, and some of them have really very powerful computers. And I think the idea of shared resources, high performance computing probably very much started at the Department of Energy National Labs. They use a lot of this, and the model for support probably took root there. I spent, 5 years at Oak Ridge National Lab and University of Tennessee. So having good amount of computing on Titan, at the time, world #1 supercomputer, as well as Jaguar. So now they have Summit and Frontier. So Summit used to be the top 1 computer on the top 500 list. It has about 4,600 nodes. dual port Mellanox EDR InfiniBand network, 250 petabyte IBM file system transferring data at 2.5 terabytes per second. So each node has 2 IBM Power 9 processors, 6 NVIDIA Tesla V100 GPUs, with a system performance that peaks at 200 petaflops for 64 bits for modeling and simulation, and peak performance on 16 bits at 3.3 exaFLOPS for data analytics and artificial intelligence. So the Oak Ridge Leadership Computing Facility Summit specs, as we see, so the performance, but also the memory per node is about 512 gigabytes, and system interconnect, which is dual port EDR at 25 gigabits per second, and processors and nodes, as we said, 2 IBM Power 9, 6 NVIDIA Volta, and with a file system of about 250 petabyte. So just as you have for the exceed allocation, so the systems that I touched on for the Department of Energy, they do have startup allocations and usually described as director discretionary allocation. So they'll give you a startup, and the focus usually will be a lot on the application that you're using, its performance, how well it does on the system, and they will sometimes have recommended applications that you can use. So that startup is for you to prepare for a larger request. I see here in the chat slide. Okay, thanks for sharing the slide. So next, still at Oak Ridge Leadership Computing Facility, we have Frontier, which is the newest and probably going to replace Summit. It's #1 in 3 categories, the 3 important categories, top 500 for performance at 1.1 exaflop, and then for power consumption as well, Green 500 #1, and as well as for AI, artificial intelligence #1 as well. So the 59th edition of the top 500 revealed Frontier system to be the first true exascale machine with HPL score of 1.102 exaflop per second. So for a very long time, we've been talking about exa computing. So you have an exaflop, truly exaflop, and through Frontier. Frontier is going to have a much better performance than its predecessor, Summit. Summit is still running, but I think they're going to be retiring it soon. So, for example, storage is 2 to 4 times perform much better than Summit IO subsystem. It has AMD Infinity Fabric, has greater than 100 cabinets and greater than 1.4 exaflops. Next, we move on to the next NERSC, still the Department of Energy. So we look at Cori. We can touch on Cori and perimeter. So Cori has about 9,668 Intel Xeon Phi kernel mini-core nodes. So you have the compute system, you have the network fabric, storage with really good connection and good performance. So Cori is designed for scientific applications, like you can see here, NAMD, app init, verbs, games, and they have more than 13.5 million lines of source code compiled, optimized, and tested. So Cori is really focused on the sciences. And so next we have Perimeter, a system optimized for science. It has GPU accelerated and CPU only nodes to meet the needs of large-scale simulation and data analysis. It has a clear slingshot, high performance, scalable, low latency Ethernet capability network, and single tier all flash lots loss-based high-performance file system. So equally, just as Cori, Permuta follows in the line of Cori, which is optimized for science. So we have fast across many dimensions, 4 terabytes per second, sustained bandwidth, about 7 million IOPS, can create 3,200,000 files per second, and it's usable for next users, about 30 petabyte usable capacity, familiar loss interface. So optimized for next data workload, new small file system with input-output improvement, new features for high IOPS, and non-sequential IOs as well. So share your thoughts in the chat. So what are the similarities, differences between the Department of Energy and Exit, or soon to be Access systems? So for me, I think the number of similarities, just in the sense that they all provide access to systems and great availability, and the allocation system quite similar, the support system quite similar. Allocation, you have a startup allocation, even though they have different appellation, but you always start somewhere. So have you noticed any other difference? Share your thoughts in the chat. So I've compiled here a list of labs, HPC centers and systems. Even though we touched on the Department of Energy, I think Department of Defense equally has a network of high performance computing, but access to those are very much limited. So I can think of once at visit at an Army HPC center, and even to go to the bathroom, you have somebody standing at the bathroom door, just making sure that you're actually going to the bathroom as you said you were. So there are a little bit more restriction by the Department of Energy. As long as you meet the Department of Energy Office of Science mission, you will have access to the system. Next, the science gateway. So we've become used to, so if we have big systems, we need to have ways to access these big systems. So, and the way to do that is a science gateway. So the science gateway simplify access to computing resources by hiding complexity. It provides higher level user interface, especially. We see that for Exit, you have a single sign-on, user access, you can manage your allocation, you can add users. You have the science gateway could also be developed by community to meet the needs and provide set of tools, applications, and data that are integrated via a portal. So, and so if you are building a website that serves your discipline or your institution or your region, or if you wish to connect with and learn from others doing same thing, the Science Gateway Community Institute is there to help you. So it's at the University of San Diego. So they can help you provide developer support, community engagement, exchange, scientific software collaboration. So this is the link to their website. If you're interested in something like that, you can join their community engagement session and you can ask all the questions. They are very good at helping users with their needs. So there are a number of Science Gateway. Actually, there are so many of them. If you visit the Science Gateway Community Institute website, they've done a good job of cataloging all of this. So if you have need for a Science Gateway or something that you can move, you can set up for your users, that is the place to go. They're well organized. I check other sites, they have this set up, but when you click on the link, it leads you nowhere, except the Science Gateway Community Institute. I only have a few misses, which is really impressive. So you have a number of Science Gateways, some that we are very familiar to. So the Open On Demand, for example, that most of us are aware of, and users like it. Amos Gateway, Anect Data, Microsoft Research Open Data as well. And this is an example of a science gateway, something that I help my users like. This is the Open on Demand portal for University of North Carolina at Chapel Hill. So, so within that gateway, you can see the listing of all the applications available on the clusters, and you can equally access your file system or the HPC file system from your desktop. Sometimes you have users who won't use the HPC because they're not comfortable with the command line. So this is something good for them. Next, ESNet and Epoch. So ESNet is a high performance unclassified network built to support scientific research. It's funded by the US Department of Energy Office of Science and managed by Lawrence Berkeley National Lab, and provides service to more than 50 Department of Energy research sites. As you can see, it's a network, has a number of networks with various performance, connecting various sites, makes it easy to move data between the various hubs. So ESNet provide technical and consulting services. So Science DMZ, if you're building one, this is a very good place to find information to set up your Science DMZ, or to build, design your data transfer node, understand persona, or set it, configure it, even get advice on how to get the hardware, what type of hardware you will need, data transfer tools and platforms, modern research data portal, network requirement gathering, collaboration, training programs and workshop, knowledge base. Their website has a number of publications that you can make use of. CI engineering launch and learn series, which happens regularly. You can sign on for one of those if you're interested. So this is the link to their technical and consulting services. Epoch, just as you see here, Epoch stands for Engagement and Performance Operations Center. So it's a roadside assistance and consultation service. They help with application by having to work more closely with application community, understand full workflows for diverse research teams in order to evaluate bottlenecks and potential capacity issues. So network analysis as well, they can help with your network through a net stage, data mobility exhibition. This was really one good for us. So test how well data transfer node is performing, provisioning of managed data service via support through IU Global NOC and their regional network partners as well. So they coordinate training to ensure effective use of network tools and science support. And one very important service that they provide is what consultation on the CC Star grant. So if you want to include them on their proposal, you can contact them and discuss the parameters of your collaboration. So another important organization is Internet2, which we are all familiar. We probably are all familiar too. So Internet2 is a community. It's a community made up of what? Higher education and research institutions, government entities, corporations, and cultural organizations. So, it is a cyber infrastructure provider or intermediate or negotiating with others, cyber infrastructure service provider to help with the members of their community. And we know one of the services that we are all familiar with is the InCommon that provides security and privacy, identity and access management tool for research and education, single sign-on, that now our researchers can move from one institution to the other and move going along with their credentials. Thanks to Internet2 and InCommon. So Internet2 by the numbers, so it's really, I think, very successful organization, 320 plus higher education members, 950 plus Ethereum subscribers. We can go from one campus to the other and still have access to our institution internet. and net plus subscriber 350, and the number goes on and on. So it's pretty impressive organization. So Internet2 has services. I'm just going to name the three of them. There are many more, and you can check your service catalog if you need any of those services. The cloud, AWS, DocuSign, well, thanks to COVID, we are all aware. We know what it is. In common with co-manage, which is really good. Co-manage, you manage your users, groups, and access to resources. Networking, Internet2. So my first interaction with Internet2 was through networking. And next, we move to some international organizations. So I'm going to pick a few. Compute Canada, just like the Canadien, un peu de français s'il vous plaît. Calcul Canada, service et expert, découvrez Calcul Canada en français ou en anglais. So I'll continue in English, not in French. But if our Canadian friends are here, give shout out to you. So Compute Canada is an organization that that's similar to Exceed or other service providers in the US, but this looks, it gives access to computing resource. It has a well-organized portal. You have account management, resources available, how to access those resources, where to get technical support if you need one. So well-organized structure. So if you're looking for an account, you just go to account management. If you're looking to get an allocation, I think accessing resource allocation. And it's competitive. You apply for resource allocation through the portal. So, and it seems like they have an annual bid for resources. So other international organization, GIAN, by its French acronym, they provide services. GIAN develops and operates a range of connectivity, cloud, and identity service. It's similar to Internet2, and identity service that ensure a safe and secure environment for researchers, educators, and students. Just as Internet2 builds community, GIAN does similar things. Community program facilitate collaboration and knowledge sharing between national research and education networks, user organization, research and education institutions, and as well as the commercial sector. So it has a mission, which is the collaboration of European national research and education networks. Bring them together and deliver information ecosystem for infrastructure and services to advance research, education, and innovation, not just locally, but at a global scale. So ensure digital inclusion. So they have 50+% increase, bringing fiber connectivity to more European research and education institutions. Ensure data growth, on average 30% increase, average annual increase in networking per year. And of course, this is a map graphical representation of GIAN, especially GN4 phase 3 network project. So as you can see, connection connects almost every part of Europe. You have fiber, you have spectrum, connected regional network, and lease capacity as well. I have a few minutes. I think I'm nearing the end of my presentation. So praise. Just as you have GIAN for networking, you have PACE, which is Partnership for Advanced Computing in Europe. So it has the mission is to enable high impact scientific discovery and engineering, research and development across all disciplines to enhance European competitiveness for the benefit of society. So the infrastructure support, you have HPC in Europe portal, there's a portal for that, or HPCs sites available in Europe that are available to users. It connects industry, small and medium-sized enterprises, provide training and support for the users. So SPRACE is an important organization as in providing high-performance computing and other resources. Share your thoughts in the chat. What is a cyber infrastructure tool? I know there are a number of definitions. I know 15 at the end. Henry, I think I only have about 1 or 2 slides, so I'll just go over this if that's okay with you. So share your thoughts in the chat. What is a cyber infrastructure tool? What do you think? What is your definition? So I found something interesting on the National Institute of Health site. As a rule, any tool that can, tools can be characterized as devices that help scientists do what they know they must do. So if it fits that definition, according to the NIH website, Institute of Health Library, then that will be a cyber infrastructure tool. And to that regard, we have Open on Demand, Ask Cyber Infrastructure, which is I think of it as a knowledge sharing site. So if you, Axia is a place where you ask questions and get answers. Volunteers answer questions, concern, share knowledge. And then Globus is really for data transfer, sustained data transfer. You can start a file transfer, go somewhere, come back, and still have it running. So XDMode, which is XDMode, Matrix on Demand as well. Most HPC systems have this. You use that to collect metrics on how your system is being used. Grafana and Prometheus are very popular these days for collecting usage data. We have Pegasus as well, which is a workflow management system. And of course, we have the Jupyter Hub, which is very common, especially for data scientists and for facilitating workshops. I'm grateful for your attention. Thank you very much. I'll answer questions if there are.
All right. Thank you, Jacob. That was fantastic and very helpful. Quick announcement, which is to say quick brag. I'm happy to report, first of all, that yesterday we had 275 attendees. And I can also report that taking into account some folks who are participating today, we now have covered 98% of R1 universities and 77% of the R2 universities that have on-campus centralized research computing resources. So we're doing really, really well. Lots of non-PhD granting institutions, lots of minority serving institutions, lots of institutions in EPSCoR jurisdictions, and lots of institutions all around the world. So I am super stoked, very excited. And we are coming back at quarter till, and our next session at quarter till is going to be how to do an intake interview, including intake interview demonstrations. And this is going to be led by Dirk Colbrey, the principal investigator for the Cyber Ambassadors Project. So this will be a very exciting session for all of us. I look forward to seeing you there. I'm going to go ahead and stop the recording, and we'll see you in 25 minutes. Is that right? I think that's right. All right. Thank you, everybody. And thank you very much, Jacob.
No problem. Okay.